Okay. Yep. This is the folder we were working in last week. So I discovered that there was a typo in the script, and I'll show you what it was. It was included in that upload I sent out just like an hour ago, but oops. Yeah, right. So this in here, it said A plus B plus C, and B was the unrotated monomer, right? So we had one monomer that we were leaving out or putting in, so that was A, and then here we had B instead of BB. So it was producing. We weren't really getting much dynamic data in the data set. So I went to refine it, and I did the GMM on it, and it was like, it's not producing any motion. What's going on? And yeah, that turned out to be the issue. Anyway, so if that's fixed, then you can rerun this, or you can just use the data that I sent around, which was computed. That's all we needed there. So the data that I sent around, basically I took the, let me go back a folder, right? So I took the results of running that script that we put together, and I made this folder called Recon. And inside Recon, you'll find a particles folder, and that contains the results of the particles that we had generated in the folder up one level. There's an info folder, which just when I started out just contained the basic angstrom per pixel value, voltage, all that stuff. So let me just run E2 Project Manager so we can look at that. So if we run E2 Project Manager and we edit the project, right, we can see. So I filled in that stuff there, and then we ran the CTF auto processing on the data with the high resolution option checked. So if we look now in particles, we'll see the standard sorts of files that you get from EMAN after you do the CTF processing. So this is the original raw image. Then we have the full resolution version, then the LP12, LP5. And then at the end of the session last time, I was running refinements on this. So the folder I made here, rather than actually running a refinement, since I just regenerated the data, rather than running a refinement, which might have taken an hour to run or something like that, I just took the existing orientations that we had from the data. So each of these particles has the orientation information embedded in its header already. And that's the information that would get overridden if you ran a refinement. So if we say E2 display, and we look inside particles, and we look at one of those particles files and info, and then if we look at the header for one of the particles inside one of those particle stacks, you can see there's a transform.projection in there. Normally, we wouldn't use that for anything. Normally it wouldn't be present in the raw data because we hadn't computed it yet. But since it was simulated data, we already know that information. And if the information isn't provided by any other source, if it's not in the LST file, then the information will get drawn from the header automatically. So basically, after running the automated CTF correction, what we're left with is the files in sets, which contain a set for each of the different types of particles. And then the sets just point back to the individual particles in each of the individual files. And often, if you would run a refinement or something, the LST file that we'd be looking at would also have a JavaScript thing out here, which would contain any additional parameters that needed to be overridden in the header or something like that. In this case, it's already in the header, so we don't need it for anything. So then I made this sort of mock 3D reconstruction folder. So this is mimicking the new reconstruction pipeline, which doesn't make any class averages or anything like that. So basically what I did is I copied one of the sets, one of the LST files from the sets folder, and just called it particle00.lst. And then I made another copy and called it particle01.lst. Particle 00 is the the seeding LST file, the LST file for the that's coming into the refinement operation, and then this is supposed to be the result after one round of refinement. Then 3D00 is again just the initial model basically, and I didn't bother generating even odd versions of that. Then for the 3D01, this is what we're going to actually be using to sort of seed the Gaussian mixture model. I split it in even and odd halves, and I did a make 3D for the even half and make 3D for the odd half, and then I ran the post-processing script to make this. So if we look at what we wound up with there in the R3D folder, again, this was just trying to mimic enough of what you would see after running a refinement that the Gaussian mixture model program will find the files that it needs. Basically, it needs the LST file here, and the LST file needs to have embedded particle orientations, or they need to be in the parent particles, and you need to have the 3D file here. And it actually expects to see the even and the odd versions of that, which it combines together. So if we look at the final reconstruction that I got from that, it looks like a very nice GROEL structure, although you'll notice the subunit, which was only there half of the time, has much weaker density. And the subunit where things were moving around, this subunit right here, you can see how it's kind of smeared out, right? So if we look at this subunit, you can see it has lots of nice features. You can see the alpha helices. You can see like that there are 3 alpha helices right here. Whereas if you look at this one, you can see it's kind of all smeared out and stuff. And that's because we just averaged together all of these different moving subunits. Okay, does that kind of make sense to everyone? I know I sort of said all of that kind of quickly.
So you were essentially doing it manually because it wasn't an actual particle set, and so that's why you were discussing making the folders.
I did it manually just because I only regenerated the new data set a few hours ago, and I didn't have time to rerun a refinement.
Gotcha.
There's also the fact that if you rerun a refinement, you might run into the issue that it's not going to always manage to align the missing chunk to the right place, and it might not always align the moving bit to the right place. So if you have a particle that's missing one of the subunits, it's going to rely on there being in the iterative refinement that there's a weaker subunit that it can align that to. But if the subunit isn't missing in a particular particle, then that's not going to help at all. It's basically just going to align, in terms of that, it's just going to align anywhere if it's there, which is fine. But then the one that's moving, the one that's moving, if it's only out of position a little bit, it doesn't look very different than its neighbor and that sort of thing. So I guess what I'm saying is, if we had tried to run a refinement on it, I can't predict what fraction of them would have gotten aligned with the correct symmetry related orientation. If we weren't doing this with a highly symmetric molecule, if we were doing it with something like a ribosome and moving a chunk of the ribosome around or something like that, there wouldn't have been any issues at all. But when you deal with symmetric particles, which have symmetry breaking artifacts, then you have to jump through some extra hoops to kind of handle some of those details. A typical strategy that you might use is you'd actually make, since we have 14 copies of the subunit in here, you might actually make 14 copies of each particle in the 14 possible different orientations that it might be in, and then treat that as a data set. And then you just do like the dynamics analysis on one single subunit or something along those lines. There are a variety of strategies to handle it. In this case, we don't have to worry about it though, because we know the orientations, so we can just put them in where they go and pretend, and everything will be okay. Okay. This is really just sort of a toy problem to sort of talk through some of the stuff that's involved. So this R3D folder basically has the stuff that the Gaussian mixture model program needs. It has particles with orientations, and it has an even and an odd 3D map from some pretend refinement iteration. I think that's all it needs. It probably also looks at the the parameter file, which contains the refinement parameters. And I just copied this from some other refinement run that I'd done. So it actually does have refinement parameters in it. They're just meaningless. They weren't actually, I mean, these weren't actually parameters that were used because I didn't run a refinement. Okay, so again, I'm in my normal kind of project folder here. And this is kind of what a project folder would look like if I'd done one of these new style refinements. Obviously, I didn't have to make an initial model in this case either, because I wasn't doing a refinement. If I'd done an initial model, I would have had another folder for that. But otherwise, it's basically what it would look like. So on to what we were actually going to talk about today, which is this Gaussian mixture model stuff. I guess I should probably not assume that people know what the hell I'm talking about when I talk about the Gaussian mixture model stuff, and maybe I'll introduce that too. You'll note when you run the GUI version of this program, it gives you this warning: this program is still experimental, blah 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 blah, and it's very much true. It's still something that I'm actively working on. If you look at Muyuan's tutorial for the Gaussian mixture model online, it involves using the GMM through a Jupyter Lab session, not through a graphical interface. It makes far fewer assumptions and requires you to understand a lot more about what's going on. So if we go to, oh, look, my homepage. My very out-of-date homepage. So if we go to eman2.org and we look at written tutorials, there's a tutorial in here for 3D variability analysis using Gaussian mixture model in deep learning. And if you actually look at that tutorial, you can see there's some command line commands. And actually, okay, I guess he did convert it also. At least it's all running stuff from the command line. But he doesn't talk about the GUI at all because it didn't exist when he wrote this tutorial. All right, so let me just find the presentation that I've got about the Gaussian mixture model, and I can go through a little bit of that just so people know what's going on. I think maybe this. Let's see what this has got. Okay, yeah, this is just a really quick summary. That's good. That's exactly what I'm looking for. So maybe these may be movies. Yeah, so our goal is to take heterogeneous population of dynamic particles and be able to pull out this sort of motion pattern from them. So that's the final goal of the Gaussian mixture model. It should be able to deal with both discrete variability and continuous variability. So the basic idea is you take some three-dimensional object and you'll decompose it in terms of a set of Gaussians instead of voxels in space, right? So we'll break down the density in terms of a set of Gaussians. There can be a lot of Gaussians or there can be a few Gaussians. It depends on the level of detail that you're after when you're trying to characterize the motion. So if the only motion you want to look at is really coarse motion, then you really wouldn't have any need to use more than, say, 6 Gaussians at these centers of mass. If all you want to do is sort of see the relative motions of those centers of mass. If you want to see a 2 alpha helix bundle moving around in space, then you need to use enough Gaussians that feature is represented by at least a couple of Gaussians. So you sort of pick the level of detail that you're after. Then the idea behind the Gaussian mixture model is, let me just see. Right. All right. So here we have an actual raw particle. This isn't simulated or anything. This is an actual raw particle of this fatty acid synthase molecule. So the idea is we sort of mimic the molecule itself in terms of these Gaussians. And for a given set of Gaussian locations, we can then make a corresponding projection, which, if we have the Gaussians in the right place, should nicely match this, aside from noise. So we can compute a Fourier ring correlation between this and this. And as the Fourier ring correlation gets better, that implies that our Gaussian coordinates are more accurate, right? So that's sort of the error that we're trying to reduce, is the Fourier ring correlation between Gaussian projections and individual particles in known orientations. So we're assuming going into this that we have at least some initial orientation for the particle. All right. Now, if there's, yeah, ask.
Yeah. So I understand you picking the number of Gaussians, and then is it going to determine where those Gaussians are, just hierarchically, like based off of density? Like, how then, are you telling it?
The process is conceded with a single consensus 3D structure. So you make a 3D map basically from all of the data, which is going to include any blurring or anything else that might be around. And then the 3D Gaussian model that you start out with will be built on top of that. And we call that the neutral model, right? And then the motions of the Gaussians are treated sort of like perturbation theory in physics, if you ever got that far in physics, but it's basically their deviations from those neutral positions that you got for the overall map.
So I mean, like,
go ahead.
Well, I just mean, like, let's say, you said you choose 6 Gaussians to correspond to this molecule. Let's say you chose 5. How is it going to determine where the centers of mass are for that? Is it just, that's kind of what I mean.
So there are 2 strategies for doing that. There is one strategy which will sort of deterministically find centers for things. And there's another strategy which you can use, sort of an energy minimization thing, which will find the 5 Gaussians which will most completely represent the volume. That
Gotcha.
Obviously no representation is going to be a perfect representation, but you can do sort of an energy minimization using this kind of strategy, but in 3D, to find the set of Gaussians which would best match. That's not the strategy that we're typically using here, and I'll get to that.
Okay.
So you can see here, for example, that this Gaussian is maybe a little out of place. This bottom portion is sort of a little tilted, or a little tilted that way, depending on which way you're looking at the screen. So there's sort of a tilt to this. So in other words, this Gaussian and this Gaussian may be a little bit out of place. So you can actually compute a gradient for each of the Gaussian variables with respect to the energy that you're computing here. So, or the other way around. So the amount of change in energy with respect to the change of any of the coordinate positions here. So you can compute a gradient which would basically push this Gaussian towards the position that it appears to be in the image. Now the image is only 2D, and this is just a 2D projection of the 3D Gaussian map. So if you do this for any individual particle, you're only going to get 2-dimensional gradients for the 3-dimensional distribution. And that's why you can't just solve this problem using traditional linear algebra approaches. If you had 3D volumes and 3D Gaussians, and then you had gradients for each one, you could just use something like a singular value decomposition or something like that. And you could solve it with linear algebra and come up with sort of an optimal solution for how things must be moving and that sort of thing. But since we have incomplete data, something like a neural network allows us to kind of say, okay, we have this information, but this information is just completely unknown, which is very hard to specify with linear algebra, things that are not known. And that allows us to kind of solve this problem via energy minimization. So the strategy we're using in deep learning is kind of like an autoencoder. It's not actually an autoencoder. In an autoencoder, the idea is you take some input and you put the same thing that you have in the input at the output. So if you have like a noisy image, you can put a noisy image in the input, and then the goal here is to produce the same noisy image in the output. But then you have a deep learning structure, which is getting smaller and smaller and smaller. So you may take your 5,000 pixel image or your 100,000 pixel image, and then in the middle of the network, you may be reducing it down to, say, 5 different values or 10 different values or something like that. So a very small number of different numbers that might be here. And then those numbers somehow have to reproduce the entire image. So in an autoencoder, the network connection weights are basically learning the structure of the images that you're teaching it. So you put in not just one image, but you put in a whole bunch of noisy images, and each noisy image you train So it tries to make the output look as much like the input as possible, given the fact that it can only base its answer on the few numbers that are available here. So autoencoders are the deep learning equivalent of doing something like principal component analysis. It's designed to identify a few characteristic numbers which are most representative of the differences between different sorts of images, or different images within a common set.
I'm sure it's wildly inefficient, but could you use this to make files smaller?
No, because the network parameters here, which are kind of hidden, every pixel here is connected to every pixel here. So here to here, you have an n² relationship, right? So the number of parameters in the network is humongous. So yes, you could use this as sort of a reduced representation for images, for sure. But if you're talking about sort of saving disk space or something like that, to recover the images themselves, you'd have to store the network, right? And the network is massively larger than the size of even a fairly large set of images. So right. So the strategy we're going to use here is kind of like an autoencoder, but it's not actually an autoencoder. So the strategy we're going to use here is we're going to, for each particle, someone needs to mute. Okay. We'll compute the gradients, like I just described, for each particle with respect to the neutral model. So instead now of having an image, which may be 1,000 different values or 10,000 different values or something like that, instead of having an image, now we have, if we have m Gaussians, we now have m times 5 parameters. So each Gaussian has x, y, z coordinates. It has a width and it has an amplitude. The width is actually something we've gotten rid of now, so it basically has m times 4 parameters now. But anyway, you have three coordinates and you have an amplitude. So if you have 6 Gaussians, you've converted your 10,000 variable image now to something which only has 6 times 4, 6 times 5, 30 parameters. And so that becomes basically this set of gradients becomes a reduced representation of this noisy image itself. And that reduced representation is what goes into the neural network over here. Okay. So you then put that representation of the image, or how the image is different than the neutral 3D map, into the network. That gets reduced and reduced down to some reduced representation space here called could be called the confirmation space, could be called the latent space. There are different names for this. Typically, the default value here is there's 4 dimensions here, just 4 different numbers here. And then that expands back out, and it will produce a set of, again, m times 5 or m times 4 Gaussian locations. So what you put in are gradients of an image with respect to the map, and what it's going to produce is a full 3D Gaussian representation of that particular particle, hopefully. So you put in just 2-dimensional information. What you get out is 3D information, and the network is supposed to learn how, as a whole, all of the different 2D particles. So all the 2D, when you train the network, you're basically training into the network that 3D aspect of it. So then you can put just a 2D particle in, and you can get a 3D version of the particle out. So when the 3D version of the particle comes out, you can make a projection of it. You can compute the Fourier ring correlation, like I was just talking about in the previous slide, and then that becomes your score. And when you're training the network, what you're trying to do is you're trying to minimize that. You're trying to reduce the difference between these particle parameters that you're putting in and then the actual particles themselves. So when you do the comparison here, you're actually going back to the original raw particles. You're comparing the projections of the 3D Gaussian coordinates to an actual particle image, not this. It's just that this is producing a proxy to go into the network. All right. I realize that's somewhat complicated, and my goal is not to turn you into deep learning experts in 10 minutes here or whatever. But this is how we sort of structure the problem. once you've trained the network, you can then put a particle in and you can get a 3D structure out. And you can also look at the coordinates of that particular particle in the latent space. So let's go back here. And what I'm going to do now is go through this GUI a little bit. It's still under development. I can show you how you would use it right now, but things are likely to continue changing over the next few months at least. So the first thing I need to do is go ahead.
You say maybe we'll add a Q splitter to it, right?
Yeah, maybe. All right, so the first thing to do is hit the new GMM button. So we have to create a GMM folder for the project, and the input to that is going to be a result of a refinement. It could be a new style refinement, it could be an old style refinement, and now it's actually I've just started making this work now with tomograms. So you can, if you're doing subtomogram averaging, it will now not break if you try to use it with a subtomogram average, although still some work needs to be done to get the results optimal. So you pick the folder like that, and then it will automatically process the contents of the folder to sort of seed this Gaussian mixture model process. This isn't doing the network training or anything like that. It's just setting up the project as a whole. And maybe I should bring the terminal window out somewhere where we can see it, because that's where, yeah. So we can sort of see what's going on. All right, dragging isn't working right. Oh, that's not working right either. Interesting. All right, well, we'll just wait till it finishes now that we've got it in the front. Surprised it's taking that long. It should be pretty fast. Oh, maybe there we go. It wasn't in the front. Okay, now it's done. Now let me bring that window back to the front, and I'm going to just move it down a little bit here so we can see if it's doing anything in the background. Okay, now I'll click on that, and we still won't really see anything. The next thing we have to do is create a run. So within this GMM folder, you can do multiple runs, and the runs allow you to explore different numbers of latent variables, different numbers of Gaussians, different sort of resolution levels, and that sort of thing for a single refinement. So this GMM is basically a representation of a single refinement run, but then you can explore it in different ways. So we'll create a run, and I'm just going to call it test 1. Give it whatever name you want. And now we will see a particle volume appear. So this is the neutral structure that we just looked at a minute ago, right? So you can see the missing subunit there, and we can see the blurred out subunit right here. And now we need to sort of pick our parameters for training the Gaussian mixture model. So the way you just sort of decide how many Gaussians to put in is you don't say, I want 50 Gaussians. You tell it what resolution you're interested in targeting. And here maybe we'll start with, say, 20, because it'll run pretty fast with a low resolution. And then you have to give it a threshold value. So if you want to have more Gaussians, you lower the threshold value. If you want to have fewer Gaussians, you increase it. For a low resolution map, I'm going to start with a really high threshold, like 0.8. This is on sort of a 0 to 1 scale, roughly. And then you hit the resolution button, and it will compute a filtered map at that resolution, so you can sort of see what it looks like, and it will put Gaussians in it. So you can see it has 77 Gaussians, and you can say, well, I don't see any Gaussians. Where are the Gaussians? Well, they're hiding underneath the isosurface, so I can make the Gaussians bigger if you're doing a coarse model here. If you're doing like a high resolution model, the default Gaussian size, it'll show up pretty quickly. So you can see how coarse the representation we produced is. You can also tell a little bit from the number of Gaussians. So is this too coarse, or is this about right? Well, there's an issue here, right? You'll notice that we don't have any Gaussians in this sort of missing subunit. Once we've sort of blurred it out here, it's basically, it looks like empty space here, or almost empty space. So we didn't get any Gaussians there. So we'll probably have to lower the threshold a little bit. That'll give us a few more Gaussians at the same level of detail. And now you can see we've got at least a couple of Gaussians here, which are occupying that kind of missing space. we might still run into some problems finding it that way. And I'll also point out that mixing motion and discrete variables in a single run sometimes also has some issues. It'll probably be a little more pronounced than usual since we've done such an artificial example here where we've made really smooth continuous motion and we've taken a really big chunk and kind of put it in. Anyway, we'll have to see what happens when we run it. I don't have super high hopes that I expect we're going to be able to see the motion easily. I'm not sure whether we will as easily detect the presence absence down here, even though that seems like the easier thing to find. I could make it a little bit lower, but I think 128 is probably a reasonable starting point because I don't want to spend a really long time on this. The computer that I'm running this on is my workstation at work, so it's got a single NVIDIA 2080 card in it, which is pretty fast, but it's not as high end as some people might have on their workstations. Right. So I've picked my parameters. I also, before I start training any networks, I also want to make sure all the stuff down here is correct because you have to retrain the network if you make any changes to the stuff down here. So I don't want to use a mask. It defaults to sort of taking the mask, if there was one from the refinement project, and then copying that in. Since I don't have one at all here, it's kind of dangerous to leave that. But probably you often you'll want to erase that. You can use a mask, which just sort of defines a particular region you want to focus on. But I would say that process is still not optimal. We have to pick how big we want the latent space to be. 4 again is the default. We have to pick a number of training iterations. 10 is kind of on the light side. I'll go for maybe 20. There are cases, particularly if you want to learn sort of subtle motions where 50, 60, 70 training iterations might not be a bad idea. This is a model regularizer. So if you make this number big, it will try and prevent the dynamics from moving too far away from this neutral state. So if you're looking at really subtle motions, you can use a big value here, and it might prevent a situation where maybe this Gaussian might swap position with this Gaussian or something like that. But most of the time, it's not really necessary. So I'm just going to set that to 0. This is sort of how much it perturbs the model while it's running. So it has to jiggle the model a little bit to sort of explore the possible conformational space. And this sort of defines the level of jiggling. 0.1 is the default, and it's not a bad choice for most things. Hopefully, when we finish, the range that we're expecting to see in our final results, which are blank right here, right now, the range we're expecting to see is sort of -1 to 1. So 0.1 is on that scale. And we hope to see variations on the level of sort of 0.2, 0.3, something like that. So that's often an okay value. There is an alternate network structure you can use where you use a convolutional neural network instead of a regular neural network. It doesn't really make any sense that works, but it tends to work and it tends to run faster. But I'm not real fond of it still, so I turn that off. And then you have to pick whether you want to allow the position, the amplitude, or the width of the Gaussians to vary. Like I said, I've gotten rid of width now in some of the newer things, so that eventually is going to go away. We'll go ahead and let both position and amplitude vary here. If you want to detect this missing subunit, that should come through as an amplitude variation. If you turn off amplitude, then it will try and deal with any missing subunits by basically taking the Gaussians, which are in that space, and pushing them off to the side or something like that. If we give it the freedom to alter the amplitude, then hopefully it would take care of it that way. So that's about it. So we've got, and the box size is preset. That's the size of the particles we generated. Angstrom per pixel is preset. Symmetry, if you impose symmetry here, right, then that it wouldn't work very well because the things we're looking for are breaking the symmetry. So we don't want to have symmetry specified here. And then we talked about everything else.
Is it worth explaining why sigma is going to be taken away? I assume it just wasn't useful
There's a
parameter?
practical reason and a mathematical reason. The practical reason is it's just not really very useful.
Right.
I mean, it kind of goes against the whole idea that you're picking a length scale that you want to look for changes in, and you know, you want to consider sort of a certain coarseness of resolution. So you want to sort of set the Gaussians to be some size, and that's going to define the level of features you're looking for. If you allowed the sigma to vary by a lot, then it might decide to make several of the Gaussians really tiny so they could fit in some small feature or something like that, and it would kind of defeat the purpose of specifying the scale that you're working with. The mathematical reason is that the math becomes massively more efficient if you don't allow that to vary, which allows us to make it run a lot faster. So if you ever heard me talk about this before, Muyon's original Gaussian mixture model approach had serious memory problems. You could only look at structures with a fairly small number of Gaussians, so you couldn't tackle like a high resolution Gaussian mixture model or something like that, because you'd exhaust memory on the machine. And by getting rid of sigma, I came up with a new strategy which has no problems with RAM at all. So that's why it's now possible to do this with subtomogram averaging, and it wasn't before, is because we've gotten rid of sigma, basically.
Gotcha. That makes sense.
Yeah, it makes a little sense anyway.
Well, it's good news.
I'd have to go into the math a lot more to really explain, but yeah. So all right, so we're all set. So the next thing we have to do then is train the neutral model. It used to be there were only two buttons here: train neutral model and run dynamics. This is Muyon's original code. This is my new version of the code, which doesn't have sigma and doesn't use as much memory. So we'll be using the new one. The old one is there because, you know, there's still cases where you may need to use it, and of course I don't want to disallow Muyon from running his version of the code, because he's still making his own changes to it too. So you can see down here it started running. So it's reading all of the particle data in here. So what you're doing now when you're training the neutral model is we sort of pre-train the network. I guess I can talk about this. Where did, oh, no, lost my presentation.
I recognize those images.
Yeah, progress reports. Back to this again. Right, I was using that one. So right now what we're doing is we're sort of pre-training the network using just the single 3D map as a starting point. So we're mostly training this part of the map. So if you put 0 in, what you get out is the neutral model. So 0 is sort of the neutral configuration. If nothing's moving, then it's going to be in the neutral configuration. And then those numbers that we get out from sort of -1 to 1 are going to be changes in the 3D map with respect to that neutral model. So right now it's just training the neutral model part of the network, and that's pretty fast. It's almost done now. Okay, so that's finished. Finished? Almost finished. Okay, sorry, it has to do one last make 3D. Okay, now it's finished. Once that's run one time, you can run the dynamics multiple times. So if you want to change the parameters a little bit down here, there are some parameters you can change without having to rerun the neutral map. Some you can't. If you change the number of if you change the size of the latent space, that's the layer in the middle of the network, then you have to retrain the neutral model because you've changed the structure of the network. But if you want to change the amount of perturbation or something like that, you can change that as you like. All right, so we're also ready. I already set the parameters down here, so we can also just run the dynamics now. And this is going to take a little while to run. I think it'll take less than 10 minutes, but let's just see how long it looks like it's going to take, and we can talk about something else while it's actually running. So now you can see I guess that's another thing I should point out. We had generated 10,000 particles, and this data set only has 8,750 particles. There was some sort of singularity in the noise or something like that, which made a few of the chunks that I had generated bad, and I didn't take the time to go back and figure out what was going on there. So we only ended up with 8,750 sort of, good particles. Okay, so you can see it running now. So it's doing sort of an initial quick training step here first. This isn't the final thing. This is only going to run for like 10 iterations or something like that. Once it finishes that, then it'll do sort of the real refinement or real training, I guess you'd say. Let's just wait till this finishes, and then we can see how fast the longer run is going to run for. I think this is 10 iterations.
This is probably
Yeah, go ahead. You go ahead and ask a question. We're just staring at the screen.
well, I was going to just say, I mean, this would be maybe more useful for me, and this is what I've already started doing just for developmental purposes. But would it be possible? Do you think it'd be worth people's time to just quickly, like, go through the Python code and just say like the chunks that are doing each section?
We'll talk about some other stuff while this is running. I just want to know whether it's likely to finish during today, and it looks like it will. Yeah, it looks like it's running pretty fast. Okay. Yeah, we could take a quick look at the Python code. And unless someone else has another question, which will be faster to answer, I can do that too. All right, we'll look at the Python code. Let's see. Yeah, we'll just do it here. Oops, where am I? Oh, sorry, I'm in the data folder. That's okay. So the program that's running right now is called e2gmm refine point. And it's called point because the Gaussians don't have a predefined width. But anyway, that's what the version of the program that we're running right now is called. So we can take a look at that one. So these are all structured. I guess I should add myself to the credits since I sort of rewrote this now. But this is structured sort of like any other EMAN2 program, which we sort of talked about before. All the arguments are handled in sort of the same way. There are a lot of different training options and stuff like that. I'm just trying to think of what's useful to go through here. I mean, I can sort of show you how some of the neural network code is constructed. Maybe
that would be great. Yeah,
maybe that's worth talking about. Yeah, how you'd interface EMAN2 with TensorFlow. Let me find a good chunk of code here for that. You can see this isn't a tiny program. Yeah, that's loading particles. Maybe I skipped it already. I thought it was up near the top of the program. Initialize the decoder. That's doing some of the training of the network. I was just going to show you the place where the network was built. Let's see. Oops. There we go. Build decoder. Okay, so this is the code that's actually constructing the structure of the neural network itself. It uses Keras for the sort of the architecture. So we use TensorFlow, and within TensorFlow we're using just straight Keras or Keras, or however you like to pronounce it. So this is sort of a high level descriptive way of defining neural networks. If you want to define an arbitrary network with some really advanced sorts of features, you can't easily do it with Keras. But if this network structure you're putting together is fairly straightforward set of fully connected or convolutional or partially connected, or there's a set of sort of layers, sort of standard types of layers in deep learning, which are part of Keras. And if you're using a structure like that, then you can basically just say, okay, I have a layer and it's this big. Okay, I have another layer and it's this big and it should be fully connected to the previous layer. Okay, I have another layer and it's this big and it should be fully connected to the previous layer, that sort of thing. So you basically define it as a Python list, and inside the list, you put each of these layers that you want to describe. Now, the input that you would use to one of these networks once you create it is going to be a TensorFlow tensor object. And we'll get back to that in a minute, because that's the place where you have to sort of interface EMAN2 with TensorFlow. So just defining in the network structure, this is something you can find on sort of any TensorFlow Keras website. You can find lots of tutorials which will tell you, okay, this is how you build a neural network. And then each of these lines is a different layer in the network. So 3 dense layers basically meaning that every neuron in one layer is fully connected to the neurons in the next layer. And then there's a dropout layer, which will arbitrarily set certain weights to 0. And then there's a normalization layer, which makes sure none of the numbers are getting sort of out of the range of the numbers that the network can handle. And then you have an output layer, which is the result. And then the reason you have another layer after the output layer here is just so the output will basically just come out as a single vector of size n, and you might want to reshape that. So in this case, we're reshaping that to be the number of Gaussians in our model times 4. So instead of times 5, it's times 4. In the original program, you'd find a 5 here. So the number of parameters that came out in the output layer, this was basically just a single vector, which was n out times 4 values, and now we reshape it so we get it out in a more convenient form. So this is building the decoder network. There's a separate part of the code where we build the encoder network. I have to go back to the beginning. Yeah, so here's the encoder building code, and you can see it looks very much the same. It takes the input and it first sort of pre-processes the input. It flattens the input. So basically, if you give it m times 4 input values arranged in individual vectors, this will just turn it into a single one-dimensional vector object. And then we have dense layer, dropout layer, dense layer, dense layer, dense layer, dropout layer, dense layer, dense layer. And when the output of this, oh, actually, sorry, yeah, these are commented out, right? So these just these layers here. And then the output of this is not going to be out to the overall network. This takes us to the middle. So the encoder takes the input to the network and brings us to the center. And then the decoder takes us from the center and gives us the final output. And the reason we define that as 2 separate networks is because we want access to the middle layer. We want access to the values in the middle of the network directly. And this gives us a nice, easy way of doing that. If you just put it together as one single network through, then it would be more challenging to get access to those values in the center. Okay, so I mentioned that what goes into this network is basically a TensorFlow tensor object. So if we run Python from EMAN2 import star. I talked about this a little bit, like with NumPy, in the lectures that weren't recorded before we'd sort of invited everyone. So I'll just sort of cover that again really quickly. I can make a test image here. Image like that. And now A is an EM data object. and A is 128 by 128 pixels. It's just a simple sort of S-shaped test image. If I want to make that EM data object into a NumPy object that I could use, that I could manipulate with NumPy functions, all I have to do is say b equals a dot to NumPy. There are a couple of different syntaxes for that. Oh, sorry, maybe it's just a dot NumPy. Sorry. Yeah, there we go. So now B is going to be a NumPy array. And the NumPy array shares its memory with the EM data object. So you can actually alter the values in the NumPy array, and you'll also immediately be altering the values in the EMAN2 EM data object. So it's actually very nice if you want to do stuff with NumPy and SciPy, you also want to do stuff with EMAN2 functions, you can sort of freely move back and forth between them, with one caveat, which is if you modify the EM data object, that will immediately show up in the NumPy object. So if I say A of 0, 0 is equal to 2, right? So I modify the EM data object. 0, 0. And now if I look at B, you'll see that first value changed to 2 immediately. So I can do that in both directions. But if I modify the NumPy object, the EMAN side won't know that it has changed. So the statistics of the image and stuff. So if I say get the average value of the EM data object, and I make some changes to the object in NumPy, and I get the average again, the average won't change because it won't know it needs to recompute it. So if you change something in NumPy and you want to see the changes to like statistics and stuff in EMAN, then you need to say a.update, which will manually trigger an update to the statistics and stuff like that. Now, once you've produced a NumPy object, creating a TensorFlow array is trivial. You can just say TensorFlow array. I mean, the same way you normally convert a NumPy object into a TensorFlow object, you can do. Now, you don't have the same sort of memory sharing ability between TensorFlow and NumPy. A lot of the operations you can do in TensorFlow are very similar to the operations you can do in NumPy. There's a lot of commonality between those two ecosystems, but there's a very good reason why you don't have this sort of EMAN to NumPy convenience. And that's because when you create a TensorFlow tensor, very often that tensor is going to be stored in the memory on the graphics card on your computer, not in the main memory on the computer. And those two memory environments don't always talk to each other easily. Okay, so when you've produced something, it turns something into a TensorFlow tensor, TensorFlow will decide whether that object needs to live in system memory or whether it needs to live in other memory. So you can't just have these sort of joint objects. Sorry about the cat. He's probably hungry.
It's always after an hour. It's funny. Yeah. It's like clockwork.
He'll tolerate me standing here and talking to people for about an hour, and then anyway, so it's very easy to go to TensorFlow as well. I mean, you can just convert the NumPy object to TensorFlow, but you won't have this easy sharing back and forth. You can also take a TensorFlow, you can also take a NumPy object and turn it into an EM data object. But when you go that way, you also don't have the same convenient sort of sharing. If you want to make an object that's shared between NumPy and EMAN, you make the EMAN image object, and then you produce a TensorFlow object from that. You produce a NumPy object from that, not the other way around. If you do it the other way around, it makes a copy. Okay, that finished running, so maybe we'll switch back to talking about that again, and then we can get more into some of the technical details in that next week, since we're running at an hour now. All right, so it looks like it ran, although it looks like it didn't work as well as it should have. It doesn't seem to have found. You can see the value differences here are very small. They're like 0.01, 0.1, that sort of thing. so each of the points that we're looking at in space here should be one particle. And what you're hoping to see is a distribution spanning sort of the -1 to 1 range. So it somehow failed to train. And I'm not sure what went wrong this time. Train iterations 20, model perturbed 0.1. Maybe I'm just going to try tweaking this a little aggressively and trying it again just to see if we can pull something out quickly. So I'm gonna increase the amount of perturbation a little bit. I will say that simulated data is often a little harder to fit than normal data because it's intrinsically not as noisy. So you have to sort of add a little more perturbation in sometimes. I'm going to turn off the amplitude just in case that's causing some issue. I don't know if it is or not. And then we'll do this again. So since I turned off amplitude, I need to retrain the neutral model, but that doesn't take very long. Anyone have any questions while we're waiting for this to run?
I'm getting all sorts of errors trying to run it myself.
Okay. What sorts? Trying. What are you? Did you download that data that I provided?
I did.
Okay. And what stage are you getting the errors at? I mean, when you do the new GMM, do you get an error there?
No error there.
Okay.
When I click create run is when the dialog box pops open and I give it a name, and it looks like it's looking for decoder, and it's very upset that it can't find one.
Okay, yeah, so that's actually fine. So when you create the run and you type a name and hit enter, it will pop out a bunch of error messages on the screen. I needed to go back and disable those. Those are printed just so I can keep track of what's going on while I'm sort of debugging things. It's not actually anything you have to. It's basically complaining that, oh, you have a run and you're trying to display the run, but there's no results for it yet. And of course, there aren't any results yet because you haven't done any runs yet. I mean, you haven't actually run the run yet. Are you getting? Okay. So you shouldn't get errors when you do the next resolution step.
I paused there because of the errors.
Yeah.
So
yeah.
I'll give that
I know. I always tell people, oh, look carefully when you see any error messages. But that was actually not an error message. It was just debugging stuff that it was printing out.
Okay. Thanks.
Okay. So, all right, so it's done the neutral. Now we need to try the dynamics one more time, and we'll see how that goes. Yeah, the cat's gone to his food bowl now, making it very clear what he wants. I'm going to run and feed the cat while this is running for a second. All right, that should keep him busy for at least a minute or two. All right. It's going. Unfortunately, you can't tell from the numbers that we're seeing here whether it's going to do something useful or not. What I've seen in the past when I've tried to run these with simulated data is either it succeeds very nicely or it sort of fails entirely. What we just saw there was sort of a complete failure case where it really just didn't find anything at all. If we don't get to a success this time, I'll just switch to where I've done a folder where I did a computation. I did a simulation previously, and we can just quickly look at that so you can see what it's supposed to look like. But hopefully it'll run right this time. It is kind of amusing, though, that the reason it tends to fail is because the data is too good. I'm not saying it always works on real data, but it won't have this kind of failure on real data. Okay, this is running pretty fast. This is the advantage of the fact that I chose a very coarse resolution and a small number of Gaussians. It'll take longer to run, obviously, if you give it 1,000 Gaussians or something to use. But to be honest, if you're looking at sort of domain motions and stuff like that, there often isn't a reason to be a lot finer than this. I mean, there's no reason to have sort of sidechain level Gaussians or something if you're looking for motions of large domains of the structure. You just add more and more degrees of freedom, and those are just distractions, basically, from the actual overall motion of the structure. So what we hope to be seeing here, and what we are seeing here, is that the number is getting smaller and smaller as it runs. Sorry, go ahead.
I was just going to say, at what point do you find that the number of Gaussians, however you want to say it, becomes an issue, like RAM-wise? You said it's not an issue memory-wise anymore, but
it should. If you're using the new programs, there shouldn't be a memory issue anymore.
Okay.
Did we get anything? Huh. Yeah, I mean, you can see it's spread out a little bit more now, but that may just because I increased the perturbation size here. And somehow it's still not. It's always depressing when a live demo doesn't work as well as you expect it to. Yeah, you can see nothing is sort of moving. Well, you don't know what you're supposed to be seeing. All right, I'm going to go to a project where I already know it worked properly, and then you'll see what it's supposed to look like. I think probably leave this one. Oops, that's not what I meant to do. This is a very similar example to the one that we did the test data that we put together. There was one subunit that was moving, and then it wasn't a whole sorry, it was only half a Gruel that I was playing with here, not a full Gruel. You can see again, there's one moving subunit, and in this case, I didn't get rid of a whole subunit. I just got rid of one 2-helix bundle up here. Anyway, you can see here, this is sort of the results of anyway GMM0. And you can see how it's spread out more. So this is going from sort of -1 to +1, and you can see sort of a shape to it. This was done with 4 dimensions. So what I'm seeing here is just dimension 0 versus dimension 1. We can look in other dimensions as well, or we could run principal component analysis and just pull out a plane like that. The yellow circles you see are maps that I computed using particles that were sort of inside the yellow circles, but projected in 4D space. That may be hard to picture exactly, but let me try a different one here and we'll just look at that. Okay, here's a nice one because I haven't computed any of those yellow circles to get in the way. So we can do the PCA or not do the PCA. You can see that it's a similar kind of shape here. If we look at 0 versus 1, or 1 versus 2, or 2 versus 3, that there's sort of 2 axes of stuff going on here. Sorry, 0. Now what I can do is put my mouse down here. I have my mouse in plane mode here. I can put my mouse down here and I can drag it. Now I don't see anything because we haven't turned on so these are all of the different things that you can show in this view. There's a neutral map, which we're looking at right now. There's a dynamic model, there's a neutral model, and then there's the dynamic map. So if we click on neutral model, this is the original configuration of Gaussians that I used. So there were 869 in this case. So this was a slightly, higher resolution one that I did here. And then if we turn on the dynamic model, these are the coordinates of the Gaussians for some particular configuration. So any point in this space, in the four-dimensional space, can represent some configuration of Gaussians. So if I put my mouse here and then I drag, you can see that subunit, the Gaussians representing that subunit, moving up and down. So that's what we should have seen in our little test experiment today. Now you'll notice the structure underneath isn't moving, and that's because the other green thing we're looking at is the neutral map. So that's just a single fixed map, right? So I can turn that off, and then we can just sort of look at the Gaussians like that. Okay, so that worked very nicely. I think in this particular case, it did not do a good job of detecting. I had something in the README file there about it not doing a good job of detecting the missing chunk that I had taken out. The color of the Gaussians is a representation of the intensity of the amplitude of the Gaussians, although that doesn't get represented very effectively, I'd say, in many cases. All right, so what we can do then, now that we see, okay, that looks like an interesting motion, is we can turn on the dynamic map. It'll come back in a minute. Actually, I'll turn it off for now. It'll turn on by itself. I can go down here, and you can see there are different modes. I was using plane mode, which is basically saying that the point that it's generating for those Gaussians is just a point in this abstract XY plane that we're looking at here. Now here, this is the results of the principal component analysis. If I go here, then it's going to be showing me the 0-axis, 1-axis plane, a point at 0. So the other two axis positions are going to be 0. If I change this to H sphere, then what it's going to do is it's going to take a sphere around the point that I'm clicking on, and it's going to average together the Gaussian coordinates for all of the 16 particles in that sphere. Now you say, why are there only 16? It looks like there's a lot more than 16. That's because it's a sphere off the axis, assuming the other two values are 0, and they're not. It's an off-axial curve. So I can change this to H slab, and what that's going to do is instead of limiting it to it's basically going to be the circle that you see in these two dimensions, but in the other two dimensions, it's going to be everything. So now, as I drag, you can see that there are 1,300 particles inside the box, or as I move out here, smaller number, 96, et cetera, et cetera. But we're basically ignoring any variations which might be represented in the other two dimensions in the four-dimensional space. Which is why people would often switch to the PCA space, because then we're just looking at one slice from the four-dimensional space, which has sort of the most motion represented in it.
Sorry, can I add just for posterity? Because I don't know if you explicitly said it. You get and for anyone watching the video, you get the e2gmm, dynamic map view by middle clicking on the mouse, right, on the 3D.
Yeah, over here, yes, I middle clicked on this to control which things I was seeing. And we'll probably add some buttons here to make that more convenient in the future or something. Like I said, it's a developmental program, but yeah, that's a good point. Okay, so what we can do now is we can make maps from the data. Okay, so I'm going to put this in fast mode. This will downsample the resolution of the map that we get out by a factor of 2, just so it happens faster, and we can make more that way. So I'm going to say map H slab fast. And what I'll do now is I'll draw a line. Oops. Oh, sorry. That's just a single map. I meant to make line. All right. I'm gonna put 1 point there. I'm going to change this now to map line fast. And now I can draw a line from here to here. And what it's going to do is it's going to make a whole bunch of overlapping spheres along that line. And then it's going to do a 3D reconstruction from all of the points, from each of the sets of points inside those spheres. Okay, so now I've got all these yellow things. I can do another one on this axis if I want. I've already got one there, so maybe I'll just draw a line there. So this is actually taking the points inside the yellow box and finding the particles associated with those points and doing a 3D reconstruction of those particles in the known orientation. So it's basically doing classification. But we can do this in a very continuous way by moving across the space. So now if I go back to plane mode, every time I move my mouse into one of these yellow boxes, it's going to update the dynamic map. So you can watch now the dynamic map as I move through space. Right? So you see all those map changes. Let me turn off the model and then it'll be easier to see. Okay, so those 3D maps that we're looking at are not representations of the Gaussians or something like that. Those are actual 3D maps computed from a subset of the original raw particle data, simulated data in this case, but the original particle data, whatever it was. Okay. Now again, it was downsampled by a factor of 2. If I go back and I do it here without the fast mode, then it will compute higher resolution, finer sampled versions of these. But this at least gives you a quick view. So if I made them overlap even more, I could make this a lot smoother. I could make the transitions from one state to the next look a lot smoother for a continuous motion. So each of these structures that I've got here is still going to have a certain amount of motion blurring based on the size of the circle that it's drawing on the screen. Now you'll see very similar tasks. So if you look at any of the other dynamics tools that other groups have produced out there, like from MIT or the collaboration with Joachim Frank, looking at these sorts of energy spaces, they all produce something kind of similar to this, where you have some manifold embedding with particles spread across it. You can sort of see where the particles are in the space and you can trace your way across it. The trick is, with any of those methods, if you want to look at the results, you actually have to compute a reconstruction from the particles. Since they lack this Gaussian abstraction, you can't look at it that way, right? So here, I can drag my mouse around freely and I can generate one of those Gaussian maps immediately, very quickly from any point in space. But if I want to compute maps, I have to actually do 3D reconstructions for each one. And it's not too bad here for 1,000 particles. I can compute them very quickly, particularly if I downsample a little bit. But if you have a 100,000 or a 500,000 particle data set, and you're computing a reconstruction from 15,000 particles for each of these yellow circles, then you're going to have this space that you're trying to characterize, and you're going to have to wait 24 hours to sort of see the results, or an hour or 2 hours or something to see the results while it does all of the 3D reconstructions. So the abstraction gives us a sort of an additional tool to sort of see, well, what should I expect to see in the maps? And then you can do the reconstructions, and if you actually see what the Gaussian model caused you to expect to see, then everything is sort of reaffirming each other, and you can be confident of your results. All right, I think that's probably it. And we've gone for an hour and 15 minutes today. Anyone have any questions about this stuff? Like I say, it's still kind of in development. You'll still see more and more changes in the GUI appearing over time, but the basic tool is there and basically functional.
Is there a good way to animate those changes, or a straightforward way?
So the individual maps that were reconstructed here are saved in a stack file. So if you just go to e2display and I go inside the GMM folder, you'll see inside each GMM folder there will be a dynamic maps stack. So in this case, 26 volumes. Doing them in order, animating them in order, you'd have to sort of load them in the correct order. You could load them into Chimera, you could load them into EMAN, however you prefer to sort of animate things, but you'd have to get them in the correct order. This, or the order that it will be in here, is the order in which they were created. Right. So if I just double click on this, it'll actually open up a 3D view like this. And if we look at the control panel, it will have all 26 volumes loaded in it. And if I grab the, so you can see them all there. If I grab the slider here, I can step through them in sequence like that. But again, that's going to be presented in the order that they were created, not necessarily the order that you want to present them in.
Okay.
But
so we could just do it in Chimera after that.
You can do it Chimera. Yeah. You could. Chimera will read EMAN2 HDF files directly. So I'm saying you don't have to convert them to MRC first or something like that. So, I would suggest you could maybe extract them in the order that you want or something like that, copy them into another file in the order that you want or something like that. And then you could load them into Chimera and just use Chimera's animation tool. Okay. If anyone has any suggestions for what to talk about next week, I mean, I can always find something to talk about. We've kind of finished the GMM thing that we were kind of planning to do. I could talk more about the details of how some of the neural network stuff works in the Python side or something like that. But anyway, if you have any ideas of stuff that you'd like me to talk about, just shoot me an email, and I'll come up with a topic for next week. If there's no more questions, we'll call this an end.
I have one quick question.
Yep, go ahead.
So you said that you had like a partially missing subunit, and that didn't come out too well in the data you were just showing.
Yeah.
If it did, or if you had like a missing subunit in addition to the motion,
yeah,
what would that look like?
In some dimension, you should see a separation. You should see a parent clustering. We've seen that. So if you look at the paper on this GMM that we published, you can see there's a ribosome example there, where there are a bunch of different, or it's not a full ribosome. It's sort of a partial ribosome example, where there are a bunch of components which are coming in and out, and some of them are present and some of them are absent. So you can actually see there's sort of discrete separations in the distribution. So if it's a discrete change, you should see a gap between two clusters on some axis, right? It won't appear on all four axes. In some axes, you'll just see sort of continuous stuff, but on some axes, you should be able to find a gap.
Okay, cool.
Yeah. Okay, that's it for today then.